Okay. All right, so we have now moved on into variance reduction techniques, or VRTs, which is an area in simulation that helps us to reduce the number of samples we need by cleverly redesigning our experiment to reduce the variance per replication of those experiments. And several of these variance reduction techniques can apply to any experiment that you design. So if you take a DOE class, you'd also sort of talk about variance reduction techniques, but a few of them are specific to simulation, and they are things that we can do only because we are the masters of our own randomness. So if we're careful, we can actually use our non-random randomness in clever ways to reduce the variance while still being able to make good inferences. And so that's what we're talking about. Announcements, ICA-L is available. That is the last ICA based on new content. And then there's this homework J2 that was originally due today, but because there's I was tardy on a couple of questions about homework J2, and because then I thought about it and that lab 10 might be actually helpful because you have to learn in lab 10, you learn how to use things like the process analyzer and OptQuest, which you definitely could use in homework 2, you don't have to. So I said, what the heck, let's just extend the availability until Tuesday night. So that is reflected on Canvas. So it's still technically due today. I put the due date in there because I still think it's a good idea to try to get this out of the way so you can focus on your final projects. But for those who do need a little bit extra time, there's that minor extension there. So that I posted about on Slack and on the Canvas announcements, even though it's not reflected in the official course notes here. So, but after J2, there are no homeworks, no more homeworks, we're done with that. And there are no more lab experiences after lab 10. So all that's done. So the rest of the class is putting together your final project and prepping for that final exam. Final project, just remember the key deliverables we're looking at are the Wednesday of the last week of class. That's when the report and the presentations are both due. The presentation is a video you upload to Canvas with your group, has a 10-minute limit. So, you know, I say hard limit. Well, if you record something and it's 10 minutes and 5 seconds, don't worry about it. I'm not going to like take off per seconds after 10 minutes, but you have to keep in mind these are going to be peer reviewed, and so you're going to peer review someone else's. So you know, you want to make sure that we basically can't guarantee that anyone's going to watch more than 10 minutes, and so that's kind of why I say it's kind of a hard limit, is that someone else is only kind of committing to watching 10 minutes of that. I have to give a lot of presentations at conferences where you know, they give you 12 minutes and plus 3 minutes of questions and answers, and sometimes people leave during that Q&A so they can have enough time to go to a different room. So if you're not done in your 12 minutes, you can keep going and bleed into your Q&A, but that might mean you're going to lose a lot of your audience for those results that you thought were so important that you needed to go beyond 12 minutes. So that's kind of what I'm just trying to enforce here, is that I'm not going to take off points if you go over 10 minutes. It's fine if you go a little bit over 10 minutes, but you know, 10 minutes is really what we're shooting for. So that's what I mean by it's a really very strict limit. It's a soft limit, but the penalty is extremely hard. And how you do it, it's up to you. So most people just open up a PowerPoint or a Keynote and they speak along with it. And with Zoom, you can be in separate places and have all 4 team members contributing just like you would in a normal class. In Zoom, if you want to be really clever, you can actually request remote control as you're presenting. And so someone else can be sharing the presentations, and you on your machine can, when it's your turn to present, you can actually get the remote control and start controlling those presentations. But it's also fine if you just say, next slide, please, and then have them go to the next slide. If you don't want to use slides, if you have another way that you want to capture your argument, that's fine. The slides are just meant to be a prop to assist you in presenting your results. It's probably smart to have some, but you could get clever. There you can record video from Arena and embed that video in your presentation, or if you want to just run some of your simulation to show how your simulation works during your presentation, that is fine as well. So a lot of different options. And then, as I mentioned, between Wednesday when you turn it in and Saturday, that's when everyone goes and gets randomly assigned one of these, and that will happen automatically, I think, the night of Wednesday. And then so Thursday, Friday, and Saturday, you'll have an opportunity to watch your chosen presentation, which will not be something from your group, will be from some other group, and then also review the 4-page report from someone else. And so you get to do those peer reviews. And I'm hoping that when you do the peer review of the reports, you'll start appreciating the reason for some of the guidelines we have. So, why is it good to have a self-contained executive summary? Well, you really want to be able to find out what the reports is all about just by reading 2 paragraphs or something like that. So, so hopefully that will become more clear as you're on the other end looking at it as a reviewer. And then peer reviews are due Saturday before the originally scheduled finals week, basically Saturday of the last week of classes. Final exam review activities, there is this ICA, which is a 32 maybe point ICA, which just samples from all the previous ICAs. You can take it as many times as you want. The highest score is taken. It is due before the final exam review lecture, lecture M, which basically is the lecture after Thanksgiving break. So that's the same lecture as the last week of classes. So so hopefully that'll generate questions for you to ask during lecture M. If not, I've got some stock slides we can go through. And then after that ICA disappears, a practice version of it will then appear immediately. And so you can still keep taking that practice one as much as you want. It just doesn't count towards your score. So definitely, I give you points as an incentive to sort of start your final exam studying before this lecture, so that you'll have questions for me during that lecture. And then so this is from last semester, and this is kind of, if on a normal semester we would have a retake structure, but because of this weird innovation week thing, then as I mentioned last time, it's a 2-stage exam. There's your individual exam that will be on Thursday of the last week of classes, and you'll get 90 minutes anytime you want during that day with Respondus Lockdown Browser plus Monitor to take it by yourself with just your 2 sheets of handwritten notes and some scratch paper and maybe a calculator, and you have all those things and you take it individually, just like the midterm. And then on Friday, then you get the exact same test again, but you don't have to be in a lockdown browser. You just get 24 hours for this open book test, and you're allowed to collaborate and encouraged to collaborate with other people in the class. And then, so then that hopefully will allow you to say, when I took the individual one, there was a particular question that I just wasn't really quite sure about. Does anyone else have any thoughts on that? And then you can hopefully learn from each other and make those corrections. I say corrections, but you have to take the whole test again, but you take it, it's the exact same test, identical in questions, but you get open book and open notes for the second round. 80% of your score comes from the individual, where you don't have notes. 20% comes from the group, where you've got access to other people in the class, as well as your notes. If Thursday and Friday you're really busy with exams, I have given you the option on Canvas to click on the People button and then go to Groups, and then the Groups tab under that, and then you can move yourself into a later final exam group. And that later final exam group will be the Monday and Tuesday of the originally scheduled finals week, where Monday is the individual and Tuesday is the group. And otherwise it's run identical to the Thursday, Friday case. If you elect to go into the later group, you will not get access to the exam Thursday and Friday. Likewise, if you stay in the early group, you will not get another shot at the exam Monday and Tuesday. So they're mutually exclusive. But make your selections on which group you want to be in. Everyone's in the early group by default. Make those selections before December 1st, because on December 1st, that's when I'm going to solidify them, turn them into sections on Canvas, so that one section will get one exam and the other section will get the other exam. And you'll start, your due dates will now reflect your selection of which group you want to be in. And I think that's all I've got about administrative stuff moving forward. Are there any questions? Pretty clear? Okay. All right, so as I mentioned, we're talking about VRTs. This is, I think, a really fun topic, just because it's kind of a combination of statistics and simulation and a little bit of programming. So it's kind of where everything's kind of comes together. And last time we introduced VRTs as basically ways that you say, well, how the heck do you control variance? I thought variance just came out of the simulation. How do I control how variable the simulation outcomes are without breaking my simulation and breaking its match to reality? And the way we do that is by using the statistical concept of control. So, what is control? Well, control is a way of accounting for variance. And so we are interested in variance generated by differences in our simulations, in the case of a relative comparison of the simulations, where we're just generally interested in variances that are caused by the simulation and not inputs to the simulation. So it's a weird thing. This is stochastic simulation, which means we've built input models. Those are the source of the variation. But if you move from input model to input model, then that generates new variation, just changing. So within an input model, you generate variation that creates a unique outcome for your simulation. But then as you go across inputs, there is an additional source of variance, which just comes from the nature of the input, like how difficult was this input versus that input. So we don't care about the difference between inputs because we've already characterized that. Those are our input models. So variance reduction techniques are an attempt to remove variance that we know about that come from the inputs, so that we're only left with variance that we don't know about that come from the simulation itself. So that's what we're kind of doing here. And if we can manage to remove that variance, then the standard error of the mean, the SEM of our simulation replications, will get smaller. And it gets smaller because the variance is reduced, variance reduction techniques. Normally, in the past, we've talked about how you increase the number of replications to make your standard error of the mean smaller. Now we're talking about increasing your number of replications to make the standard, decrease your variance to make the standard error of the mean smaller while keeping the same number of replications. So that's what we're doing here in this section. So there are 4 different variance reduction techniques that we're going to go through: common random numbers, control variates, antithetic variates, and importance sampling. And these are the common ones. There are other approaches as well, but these are kind of the standard ones that you start. So we talked about common random numbers last time, and we've seen examples of this. This should be the least foreign, where all you're going to do is use the same random number seed into replications for, so this is in the case I've got 2 different types of simulations. I'm going to run 5 replications of this and 5 replications of this. And so I create pairs of replications, pair 1, 2, 3, 4, and 5. And for each pair, I'm going to use the same random number seed going into both. And so if the simulations are relatively similar, just with a couple of minor changes, then running the same random number seed into both is like running the same string of customers into both, for example. And so it allows me to have an apples to apples comparison of these 2, and then I can choose a different apple, a different apple, a different apple, or apples to apples, oranges to oranges, peaches to peaches. So each of these inputs are the challenges I'm giving to the simulations, and by making the random number seeds the same across the pairs, I'm sure I'm challenging the simulations in the same way, so that when I look at their differences, I subtract off the absolute level of the challenge, and I can then analyze just in general how much better one is over the other when given the same type of challenge. And it all works off of this statistical idea, or this probabilistic idea here, that the variance in a difference between 2 populations is equal to the variance in one population divided by how many reps, the variance in the other population minus something which depends on the correlation between. So there's a correlation coefficient here. And so if I can manage to correlate my outputs by giving them the same challenges, then I can reduce the variance in this estimate of the difference. And that allows me to use less pairs, basically, fewer replications. So the example of this from the muffin sim I'm sorry, I got a question here. Could I explain if and how this variance equation is uniquely used in specifically CRNs? Well, so this variance expression is just, this is just a general idea that if there is ever a way to create a correlation between outputs or to capitalize on a correlation between outputs, then this will be the effect on your variance, is that if there happens to be correlation, then when you subtract the two systems, then you will get necessarily smaller variance. In CRNs, to think of without CRNs, we would run a different set of pseudo-random numbers into simulation 1. So to generate this Y1 bar, that would be just one set of random pseudo-random numbers, or one set of pseudo-random number seeds. And then we'd have a totally different set of seeds to go into simulation 2. And so simulation 2's data would be totally independent from simulation 1's data. There would be no correlation between the outputs. That's the normal way we would run a simulation. Common random numbers puts the same random numbers into each replication of these two simulations. And by using the same random numbers, we artificially introduce this correlation. And so that is what's unique here about common random numbers, is that we are introducing correlation that would not normally be there. We would normally run a simulation, forget about those pseudo-random numbers, run another set of simulations for system 2, forget about those pseudo-random numbers, and treat each output as independent, in which case the variance would just be these two added together, the variance in one plus the variance in the other, scaled by the number of replications. In our case, we're introducing correlation, and that allows us to subtract. And the introduction correlation comes from CRN. So the follow-up question here is, so we want row 1, 2, this correlation here, therefore, to be as high as possible to reduce the variance by inputting the same inputs for this. That's right. We want this correlation coefficient to be large and positive. And if we can make it large and positive, then we subtract out all of the variance that is common to the two simulations. So, you know, we might find that, what we might find is that both of the simulations are extremely similar. So put one other way is, let's just say that you generated 10 replications of a simulation, and then you generated 10 more replications with exactly the same simulation, but they used independent random number seeds. If you just compared these two populations, there would be some small difference just by chance between these two populations. And you might think that there was a small effect in these. In fact, if you ran millions of these simulations, you might be able to detect a small effect between the first million and the second million that you ran of the exact same simulation. But if you ran the same pseudo-random number seed into your sort of fictitious pairs, so effectively if you ran 10 replications and then ran the exact same 10 replications, then you know the output for replication 1 is going to be the same in both groups. You know the output in replication 2 is going to be the same in both groups. So in that case, this correlation coefficient will be maximal. It will be, you know, there'll be 100% correlation between the two of them. And what's going to end up happening is that the variance in this is going to be 0. So in that particular case, if you try to compare a simulation to itself, if you don't use common random numbers, you might see difference. But if you use common random numbers to compare a simulation to itself, you'll get the expected result, 0 variance. So we would subtract out the effect of the different random numbers, and that's what the common random numbers does. And then we're left over with what's truly different between the two simulation models. Does that make sense? Great, okay. It's a very clever trick. First time I learned about CRNs, I was really impressed by the idea. And you did this by hand in the muffin simulation from lab 2. You were given 2 types of simulation model, one simulating a greedy model of a muffin loading operation, the other one of a nearly full model. And each one of you simulated a different schedule. And that schedule is kind of like a different random number seed. And from those different schedules, you then took that same schedule and you put one into greedy and then put the exact same schedule into nearly full. And then you looked at the difference from greedy to nearly full. And that difference was just for that particular schedule. But you then had an apples to apples comparison. For this schedule, greedy has this performance, nearly full has this performance. If I would have given you two different schedules, it would have been very hard to compare for that one schedule, or for that one schedule with greedy and a totally different schedule for nearly full, because the different schedule for nearly full might have just been an easier schedule overall. And so if nearly full looks better, you don't know if it looks better because nearly full is better or because the schedule was better. So in lab 2, I forced you, all of you, to use the same schedule on both, but each one of you used a different schedule than the other. So this here were the 10 different schedules from lab 2, all plugged into greedy. And these were the 10 different schedules from lab 2, all plugged in to nearly full. And so these are like 10 different students hand simulating greedy, and these are those same 10 different students using those same 10 schedules to hand simulate nearly full. And so because they were paired, then I can draw lines connecting. So this line here, it connects the simulation that was run by this student down here. So if I click on that, that student there, she ran greedy with this particular schedule. And this student, that same student, ran nearly full with that exact same schedule. So each line is effectively representing a different schedule. And the slope of the line represents the relative performance between the two groups for that schedule. If you want to think of it in terms of CRNs, each line represents a different random number seed. And the slope of that line represents the performance for the performance difference using that same random number seed across the two different sims. So I could also plot that in this way. So each one of the points down here, 0 through 9, these are the different random number streams. These are the different schedules. This is the schedule for people whose ID ended in 0. This is the schedule for people's ID ended in 1, and so on. These are the 10 different schedules that we did. And for each schedule, I can plot the greedy with an open circle and the nearly full with an asterisk. And I can just connect a line between them just to make it clear that it's a pair. And what I can see here is that just like in the previous slide, all of these slopes here were positive. They were all angled in the same direction. In this slide, I can see that the red asterisk is always above the open circle. And so the differences here are all positive. And so those are the pairs that I generated. And so looking at the raw independent data, it is unclear to me which population's better, nearly full or greedy, because this overlap here, there is still some overlap. And so the difference I see here might be due just to chance. But when I pair up the outputs this way, which I have to do when I actually build my experiment, I can't do afterwards. I can only do this when I've created these dependent pairs. When I do that, it makes it very clear that greedy has less time in system than nearly full, always. So the variance that I'm seeing back here, it kind of gives a hint of that, but there is still some overlap here. So I'm not quite sure. By pairing them, I reduce the variance to extract the fact that it's very clear now that greedy is better than nearly full. And if I want to make that statistically rigorous, I compare these differences. I actually just plot the differences and compare them to 0. And it's going to be the case that, and this is what this p-value is up here. All of these differences, these 10 differences, if I put them into a one sample t-test with the hypothesis of 0 as my hypothetical difference, it will be statistically different from that hypothesis. The confidence interval of these differences is going to be strictly positive or negative, depending on which one you put first, greedy or nearly full. But it will clearly show that these two populations are different. And so that's what we did on the muffin sim. And in your book, they do the exact same thing. They compare a MM1 queue, so a single server, a single channel queue with exponential arrivals and exponential service times, to an MM2, where they've bumped up the number of servers to 2. And we already expect that we would think that the performance in the system should improve as you increase the number of servers. We don't need a simulation for that. But this is just to demonstrate the power of the process. So here we've done independent sampling where they've created pairs, but these pairs are not real. These pairs are like, I had generated 100 replications of each one, and I just randomly paired replication 1 with replication 1, even though the 2 replications don't have anything to do with each other. They don't use the same random number. And what I see is that sometimes the MM1 queue is higher, and sometimes the MM1 queue is lower. And so there's a lot of variance there. I could look at the general trend and it would probably tell me that the MM2 queue has a better performance. But it's not totally clear. I can make it clearer, reducing variance, by using common random numbers. And that's what your book did. And so now the first replication uses the same seed for both the MM1 and the MM2. The second replication uses a different seed than the first, but it uses the same seed across the 2 simulation models, and so on. And now if I look across this, then what I see is that the filled black circles are always above the open circles. And so the time in system for this customer is always going to be lower if you have 2 servers. And that makes sense. It matches our expectation. But something else that I want to point out here is that the effect size is amplified, and it is you can start seeing that, like, there is a very tiny effect in performance here. Each one of these things represents how much of an increase in performance, and it's relatively small. That small effect size probably would have been washed out. Look at all of the variance I have in my outcomes here. If the true effect size is actually, only this big, I'm drawing a little line on the screen here, then I've got variances that generate huge differences here, then I'm probably not going to see a statistically significant difference. So what I'm trying to do is get rid of all this ugly variance between the replications by pairing them up together. And what that does is it reduces the background variance so much that I can actually now see these tiny effect sizes with the same number of replications. So it's really a cool approach. Okay, how do you do it in Arena? You can pull in under the elements panel up here. You can pull in the seeds block, just drop it in there. And even though it looks like an old school block, you can use it with the new ones as well. You drill down into seeds, and we've talked about this earlier. We talked about pseudorandom number generators. And under the seeds here, you can click add, and you can then add a seed here, and you can give it an identifier if you want. Or you can set this identifier equal to, I think in Arena, the default stream is 10. So if you set it to 10, then this would just make you use common random numbers for all of your streams. You don't have to set a seed value. You can leave it blank, and Arena will choose that. And then if you set this to common right here, what it does is it guarantees that it's going to use every replication. It's going to use a seed that is 100,000 more than the seed it used in the previous replication. So if you run, it's going to start all the replications at a standard seed, and then it's just going to add 100,000 for every new replication. And what that allows you to do is it allows you to run a simulation, close down Arena, open up Arena with a different simulation model. And so long as this common is set here, it guarantees that the 10 replications you run with that second simulation are also going to use the same seeds that were used in the first simulation. I think I summarized that over here. So you can do this to any stream, as I was saying, and like I just said, it's going to guarantee that replication seeds are separated by 100,000. So you can run 4 different simulation models, and you're guaranteed that if you run 10 replications of each, then all 10 replications, replication 1 will all use the same seed, replication 2 will all use the same seed, replication 3 will all use the same seed, and so on. And so that's how you can generate these common random numbers inside ARENA. And then if you do use a named stream, so let's say you only want to do this for your arrival process. So you might say, I don't really care about I want to just make sure that I use the same customers, but all the other randomness in my system, I want to be decoupled and independent. Well, in that case, you can create, instead of doing this for the default stream of 10, you create your own stream. So like I was doing back here, right here, if you create a stream called interarrival time stream, you can just call it anything. You can call it TED stream. Then when you go into ARENA, then any one of these expressions that draws a random number, its final argument, which is an optional argument you normally leave off and it defaults to 10, you can put in the name of that stream. And so that allows you to create, say, a common set of customers across simulations, while allowing the random numbers drawn for all the other processes to still churn along independently. So, so that's kind of the point of that. And so that's all that I'm summarizing here. And then what you can do is, if you've got your replication, if you've got your simulation level data that comes out of every replication, you can then pair up those replications in the output analyzer. So the output analyzer actually has a way to generate pairs or you can basically load in data sets. And here's a data set of 10 replications. Here's a data set of 10 replications. And you can tell the output analyzer to do a paired difference t-test on those two data sets. And it will just pair up replication 1 with replication 1, take a difference, and then it'll use that difference, 2 to 2 difference, 3 to 3 difference, and so on. And so that all can be done for you inside the output analyzer, or you can do it yourself. You can bring in all of the replication level data into Excel and for simulation 1, simulation 2, simulation 3, etc. And then you can create your own differences and run a paired difference t-test, or into R, or whatever tool that you'd like to use, SPSS, etc. So, so that's how we handle the CRNs. There are some downside of the CRNs, which I'll mention briefly, but I want to say, make sure, is everyone on board with the CRNs? Does that make sense? CRNs. Are there questions about CRNs? Okay. I see no microphones and no chats. All right. So there are some downsides of CRNs. The biggest downside that I'm kind of talking about in more detail here is that they don't always work. So we count on generating a positive correlation in our outputs in order for CRNs to work. We don't always achieve that. So if your two simulation models are just vastly different, then even if they use the same random number seed going into both, then you might not actually end up getting a positive correlation. Even worse, you might get a negative correlation. It might be the case that every input going into model 1 that causes model 1 a really tough time will actually be a perfect input for model 2, and vice versa. So you might be experimenting with some operations research strategy that tends to be optimized for one thing but not the other, and another strategy which is optimized in the complementary way. In those particular cases, you're going to generate more variance by pairing things up than running them independently, and that's because you're going to amplify these differences that are purely due to being unlucky with your inputs. And so you don't want to generate negative correlations, you want to generate positive correlations. And even when and sometimes you're stuck with even independent outputs, even though you've paired up the random numbers. So what do you do to see if CRN works? Well, you can do a little set of pilot runs. And so just like you would do pilot runs in a power analysis or pilot runs to determine how many replications you need, you can run some pilot runs where you do use CRN, and you can basically estimate how things would be if you didn't use CRN and compare them to when you do use CRN. So you run, say, 10 runs of your one model, 10 runs of your second model, calculate the standard deviation across your 10 runs of model 1, calculate the standard deviation across your 10 runs of model 2, and add those variances up together, or standard deviations, either way. Add those variances, and then generate pairs. So generate, replication 1, difference, replication 2, difference, et cetera, et cetera. Generate your 10 differences, and then take the standard deviation across those differences, or the variance across those differences. If CRN worked, then the variance you measure across your differences will be less than the sum of the variances you get in the individual models themselves. There'll be this synergistic effect. But if they don't work, then this won't be the case. So if you get an equal variance or if you get a higher variance, then that indicates that CRN probably isn't good for these two systems that you put together. So, so that's the downside of CRN. It doesn't always work, but you can at least test to see if it works. And if it does work, it's a very powerful, in many meanings of the word, way. So it gives you more statistical power by reducing variance. All right, any questions about that? Okay. All right, so let's do a quick attendance exercise. So I will put the link in the chat. And the question I have for you is, what type of statistical test do you use with CRNs, at least when comparing two simulation models? So there's a particular statistical test that you are licensed to use for CRNs, but not for independent replications. And it's, if you're using CRNs with two, then this is the one to use. So which one is that? That's your attendance question. All right. So then let's transition to something different. So another problem, or another way that we can reduce variance, is, so in CRNs, I could use the fact that I generated all of the inputs. And so I knew, I kind of know what the background differences between my inputs are. And I can sort of subtract that away by this clever way of pairing up replications. So there is another way to do something very similar to that. And this can be used not just in simulation, this can be used in any experiment. And we can use it when we're estimating absolute performance, not just relative performance, and that's control variates. And the idea here is that, let's say I have a simulation or any real experiment here, and I am measuring some response, a single response from that simulation that I call Y. And I know that there is some variation in Y due to variation in some independent variable that goes into the simulation called X. So in real life, X could just be an independent variable that I have to deal with. It could be the temperature of the day, could be the amount of sun that we get that day. And then Y is my output. And so I know X and Y are related. I can measure X. That's the key thing, is that you have an independent variable that you think is related to your response variable that you're interested in. And you can measure the variance in your independent variable. So if I can measure my independent variable and I have its a known mean for that independent variable, then I can use correlations between the independent variable and response variable to reduce the variance of the response variable by subtracting off a component of the variance that I am pretty sure has to do with the independent variable. So my example here that I've got for kind of a real world case is, what if I've got power generation by solar? So I've got solar power, so all the solar power here, and I want to look at power output. Now, there could be very many reasons for variations in power output. And so if I look at my power output here, this power output, it's got these variations here across the days. And so I am trying to estimate the average daily output of my solar panels. And so when I run a simulation, or I even look at real world data, when I'm estimating average daily output, then every time I run this estimation, I get a different estimate of average daily output. And if I want to know what the true average daily output is, and bring those confidence intervals down so my estimates collapse to tiny amounts there, I like to account for some of this variance. Now, I know that a major reason for the variation in average daily output of solar is just due to, say, temperature variation, or I could measure, this is sort of a proxy for measuring the amount of sunlight availability. And so, because I may not be able to easily measure how much sunlight was available on the solar panels, I can measure the temperature that day. So I can measure how hot was it near the power plant. And so my idea here is I'm going to look at the known variations in temperature and look at how they correlate with the variations that I measure in power output, and subtract off a portion of the variance in power output that I know that comes from variations in temperature. And so, and that's what I'm kind of saying here, is that if my output, which is the power output, is correlated with temperature, then I can subtract each day's power output, a little bit of it, that is proportional to that day's difference from the average temperature. So for a hot day, I can subtract off, more than for an average day. And for a cold day, maybe I end up adding some. So it's that difference so I'm actually manipulating my output response variable by controlling for the effect that seems to be demonstrated between temperature and the output. And so to make that a little bit more mathematical, then what I do here is I am trying to estimate Y, which is the output of my simulation. And this X, you can view that as one of your input models. You can view that as is just like the average delay between, or you can view X as the delay between customers, and X bar is the average delay, or something like that. Or I think it's even better here to view, you can view X as the average delay between customers for a particular customer input stream. And so you can say across all of the customer input streams that I used in my simulation study, then I got a certain average delay between customers. And I can say that for one simulation, its average delay between customers was higher than that. For another simulation, it was lower than that. And so I can, that's where this e to the x is the average across all of my simulations, and where an individual x might just be the average delay for one simulation. So the idea here is that I am taking my response from my real simulation, I am taking a measurement of an independent variable from that real simulation, and then I am taking an average across all of my simulations. And I then use those to create what we refer to as a control variate, a CV, a control variate. And it is a control variate that is going to be the original variate. So you can view this as the original response minus some scaled version of that replication's difference from the mean. So this kind of characterizes how different this particular input is for this replication from what I'd expect across all of my replications. And so that's going to generate a new random variable, which is just a modified version of the thing I actually wanted to estimate. Now, what's cool about this is that this is an unbiased estimator of the thing that I want to estimate. If I take the mean of the control variate down here, and I just do a little probability here, then I can tell the mean of the control variate is just equal to the mean of the thing I really want to estimate, plus this couple of terms which cancel out. So the mean of the control variate is equal to the mean of the thing that I actually want. So this weird control variate that I built is an unbiased estimator of the thing that I actually want. So even though I've manipulated these data in this weird way, if I can measure the mean of this control variant, it will be the mean of the thing that I actually want. So I do no harm by introducing this control variant. And now the challenge is, how do I calculate this C value, this scalar, to guarantee that the variance in this variable is minimal and less than the variance in this variable? So that's what I'm going to do here. And so what I do is I can calculate the variance in the control variate, and with a little bit of probability, you get a formula for that. And then what I want to do is just then optimize. I want to minimize the variance. And so I can take a partial derivative of this thing with respect to C. I can set that thing equal to 0, and then I can solve for the optimal value of this C scalar so that I minimize the variance in my control variant. And it turns out that it will be this thing right here. It will be the covariance, which is kind of a measure of correlation between X and Y, between my independent and my response variable, divided by the variance in my independent variable. So this basically tells me what component of the variance in the response variable is. It tells me what fraction, basically. It's saying that there is some fraction of the variance in the response variable is due to the variance in the independent variable. This tells me that fraction. And so that, if I then measure the variation, the current variance in any replication, and then scale it by this fraction, that allows me to subtract off the variance in the response variable that is purely due to the independent variable that I already know about. And what I'm left over with is less variance, but still plenty of information about the thing that I actually care about. And so that is the control variate. So this is our control variate variance right here. And the greater the correlation between the independent variable and the dependent variable, the greater the reduction. And this will always work. It may not actually produce any variance reduction, but it will do no harm, because you can see this thing squared up here. So if there's positive correlation or negative correlation, it will work either way. It will always work. And in the worst case scenario, if X and Y have no relationship, this covariance is just going to be equal to 0. And the variance in your control variate will just be equal to the variance in your response variable. So you've done no harm. You did a little extra arithmetic, but it's not that big of a deal. And so that is a way that we can handle this control variate. So I would normally do an example from Monte Carlo simulation, but I want to make sure that we at least get some exposure to the two other types of VRTs before we end class. So are there questions about the control variate? Is it pretty clear how it works? And if you want more convincing, then I encourage you to step through these slides where I do a little Monte Carlo simulation where I actually show that we can estimate the variance with far, far fewer simulations in a Monte Carlo simulation using this approach. So it has it can really make for a tight estimation of something without actually adding any more replications. So any questions about control variates? It's pretty clear what we're doing there. We are estimating the correlation between an independent variable, like something that you get from your input models, and a dependent variable, like your response variables from your simulation. And when we know how much they're related, then we can subtract off the demonstrated variation from the input model from the response model. For those of you who go on and do more statistics and you get into multivariate linear regression models, that's exactly what you're doing in a linear regression model with multiple variables, is that you're saying that I am really only interested in the way this one independent variable affects this response variable. But in order for me to really get a good idea of that, I'm going to take all of these other independent variables and put them into the mix as well. And then I'm going to simultaneously measure the effect of all of these on my output variable. And that controls for the effect of all these other independent variables. And by controlling for that effect, it allows me to better estimate the separate effect of the one thing that I really care about. If I didn't put in all those other ones, it would just be variance getting in the way. It would be noise in the way. But by formally modeling them in my multivariate linear regression, then I subtract out their effects on the things that I care about. So that's what you would see in a slightly more advanced stats class. And maybe you saw a little bit of that in 380 if you talked a little bit about multivariate. So any questions about control variates? All right. So I'll skip that attendance question for now. So we've got these last two, antithetic variates and importance sampling. And antithetic variates is covered in your book, by the way. So you'll see some book things just like we did from the CRNs. So with CRNs, that was a way for us to better estimate relative performance of two simulations. So I've got simulation model 1, simulation model 2. I want to estimate if there's any difference between these two different types of simulations. And I can use common random numbers to do that. Now, the motivation here is saying, well, what if I want to estimate absolute performance of one simulation model, not of two? Then the question is, how could I possibly do something similar to common random numbers, where I can kind of factor out the effect that is due to just the inputs themselves, so that I can better estimate the noisy the effect that's due to just the simulation. And so the idea behind antithetic variates is that by the law of large numbers, whenever we get a string of above average outputs, so response variables, responses that are really high, like really bad, they will eventually be balanced by below average outputs. And so we run lots and lots and lots of simulations. We run 1,000 simulation runs because we're hoping that if we run 1,000 simulation runs, we're going to get a mix of both. We're going to get the days where we're going to get lucky days and unlucky days together. And as long as we have a mix of both, they'll balance out and we'll get a good estimate of the average performance. If we only run 3 replications, we might be unlucky. We might have 3 bad days or 3 good days. And so the estimate of performance will be far too high or far too low. And that's why we run more replications. Antithetic variance says, what if there was a way for us to guarantee that for every good day, it was immediately followed by a bad day? And for every bad day, it was immediately followed by a good day. If I can manage to re-engineer the universe, as I sometimes can with a computer simulation, so that I get this complementary effect where inputs that are good are followed by inputs that are bad, I don't need to run as many replications, because my small number of replications will always have an equal mix of good and bad inputs. So this is our typical case here, where we've got a string of good, a bad, a bunch of string of good, and a string of bad, and so on. And so the average we're trying to estimate is 7.2, but the average of the first 6 samples is 8.7, far above 7.2. What we would like is to somehow get those sorted so that for every good, for everything that's above average, it's immediately followed by a response that's below average, and then above average, below average, below average, and so on. If we could of course, we can't just run 1 million simulations and sort them. That kind of defeats the purpose. But if we could somehow engineer the simulation, so if we ran 6 simulations and they just automatically did this, we'd be in good shape. As you can see here, the average is still 7.2 because I just resorted all those response variables. But the first 6 sample average is far closer to the true average. So by doing this sorting, so that I got a good and then a bad, and then a good and then a bad, and so on and so forth, then it gave me far more statistical power so that I could use less samples to get a good average. So how do we make that work? Well, the idea here is that we are trying to introduce, just like in common random numbers, we're trying to introduce a correlation between pairs of replications. In this case, between odd numbered replications and the even numbered replications that follow them. So I want to generate a correlation between replication 1 and replication 2. I want to generate a correlation between replication 3 and replication 4. And if I can generate, so I've got A and B here. Think of A as replication 1 and B as replication 2. So A might be your odd numbered replication and B is your even numbered replication that follows it. So I know that if that I can generate an unbiased estimator just by taking the average of every 2 replications. And so my thought is, what if I create pairs of replications, one following each other, that taken together are viewed as an independent replication? Then those pairs, then just like with CRNs, I can then compare pairs of replications to each other as if they're independent, but the pairs themselves will be dependent. And I just need to create the right dependency in these even odd pairs. And the dependency that I'm looking for here is going to end up being, I want to create a negative correlation. So in common random numbers, you create a positive correlation among parallel replications that have the same random number seed. In antithetic variance, you create a negative correlation between, in a single simulation model, between replications that follow each other. So every even replication will be negatively correlated with the odd replication before it. And so that capitalizes on this idea that the variance in the average in each one of these pairs is going to be the variance in the odd one plus the variance in the even one plus a term which is proportional to the covariance between them. So if we can make the covariance or the correlation negative, then the variance in this estimate is going to be less than the independent estimate. So that's what we're trying to do, is to create less variance in these pairs than there would be if they were independently together. So how do we do that? So what we're going to do is we view each, we recall that in every simulation, the simulation's running along and you've got these input models. And so you've got an input model for A, an input, like, so this is like the inter-arrival time. This is like the service time and so on. And you've got input models for each one of those. Inside Arena, it draws a random number between 0 and 1. And it takes that random number between 0 and 1 and it puts it into the inverse CDF of your input model for the inter-arrival times. It then takes another number from 0 to 1 and it puts that into the inverse CDF of your service time distribution and so on. It does that for all of those within your one simulation model. And so we can view your simulation model really as some nonlinear function that takes as arguments all of the inverse CDFs for all of the input models inside your simulation. And then the arguments that go into those inverse CDFs are the actual random numbers that Arena draws that are between 0 and 1. So this is our model of a simulation model, just a nonlinear function of inverse CDFs where each inverse CDF takes a number between 0 and 1. And there's a difference in number between 0 and 1 for each different input model. This is a model of one replication of your simulation. Now, the idea is, what if we run one simulation replication, and then before drawing a new random number, we take all of the random numbers that went into the first simulation, and we subtract them from 1. So this, and we then rerun a simulation using those new random numbers. So on the odd replication, we drew new random numbers. On the even replication, we pretend like we drew new random numbers, but we don't actually go through the process. Instead, we take the random numbers from replication 1 and we just take their complements. We subtract them from 1, and that generates a new string of apparently random numbers, all uniformly distributed between 0 and 1. But if this one was close to 1 in the first replication, it will be close to 0 in this replication. If this one was close to 0 in the first replication, it'll be close to 1 in this replication, and so on and so forth. So the model of my second replication, where I'm just using these random numbers which are derived from the independent random numbers drawn in the first replication, then this becomes my model of the simulation output. It's some nonlinear map with all of the same inverse CDFs for all my input models, where now the arguments are the complements of those independent random numbers. And so the hope is that by doing that, by creating these pairs in this way, where the odd ones get independent numbers and the even ones get this 1 minus, then the hope is that because these random numbers over here on the inputs, the actual random numbers themselves, the ones between 0 and 1, they are negatively correlated. And the hope then is that that's going to create responses that are negatively correlated. And so that's our hope. And there are certain mathematical conditions, monotonicity, for example, in this nonlinear map. And so if this map here, H, if it's monotonic in its inputs, then that generally means that, like, if you increase the inter-arrival duration, it will improve your performance, because you'll have to do with you'll have less waiting time. So that, if that's always the case, that the longer you increase your inter-arrival times, the better the performance you get. As long as you have a monotonic simulation model, then this is sort of guaranteed to work. And so that's what we're kind of counting on. So we are going to run these pairs, and we're going to run a bunch of them. So we run 1, and then replication 1 is independently drawn, replication 2, dependent random numbers. And then those then generate our so-called antithetic variate, which is just the response from the odd numbered replication plus the response from the even numbered replication divided by 2. And then this becomes the response variable for that pair combined. And so what does that look like? Well, here's an example from your book. They've simulated 2 different types of systems, and the filled ones are system 1, and the unfilled ones are system 1. I'm sorry, they're one type of system. The filled ones are the odd numbered replications. The unfilled ones are the even numbered replications. And they've artificially paired them up. And so they've created a pairing that they haven't done the antithetic variates yet. They just happen to do, whoa, I apologize for my scroll wheel. And so they have not accounted for the variance yet. So here, you get replication 1 is here, and replication 2 gets plotted up here. Replication 3 is here, replication 4 is plotted down here, replication 5, 6, and so on and so forth. And so they have just plotted them in this way. And then they have plotted the average between these odd and even numbered replication pairs. And what you can see is that there is the average value between these two is still pretty noisy. Now, if they turn on the antithetic variates, and then so now you've got the odd numbered replications are the independent ones, and the even numbered replications are the ones that are derived from the random numbers drawn in the odd numbered replications. And then they average the 2 of those. Then what I hope you see now is that the average in between the pairs has been significantly reduced. So if I go back, you get this ugly, bouncing line that goes everywhere, and the actual mean, and again, I apologize for the scroll wheel. Let's go go back here. So the actual mean is the dashed line here, and it's kind of a lot of variance. You know, it's not really capturing that actual mean very well. But then down here, when you turn on the antithetic variates, then that pretty much they're always floating around that mean, and it's significantly reduced. And so that's how the antithetic variates have increased our ability to make an absolute performance estimate from a single model. And I do an example with Monte Carlo simulation. Again, I'm just going to kind of skip over here for time, but it's in the slides where I implement these antithetic variates in a Monte Carlo simulation to show you how much of an improvement you can get by in reducing your variance. So if I've got a confidence interval, I've showed that I can get the half width down by an order of magnitude using the same number of simulation runs, actually half the number of random variables though, and it collapses much closer to the actual mean that we're expecting. So that's the example that I've got there. Now, how do you use antithetic variates? It's a similar process as in the common random numbers. In ARENA, you go into that seeds block, which is underneath the elements here. And then in the seeds block over here, then you can add a stream. Let me do a little arrow, maybe you can add a stream up here. Apologies for that. You click that add button right there, and then you can add a stream like we did in the common random numbers. But in the initialize option, instead of choosing common, you choose antithetic. And what that will do was it will guarantee that the even numbered replications are antithetic versions of the odd numbered replications. So it only draws fresh random numbers in the odd replications, and then it remembers all of those random numbers, and then it reuses them, but with one minus in the even number. That's what the antithetic option does right there. And that's what I'm just saying here. The odd replications have fresh random draws. The even replications are the complementary versions using those remembered ones there. You can do this for the default stream, or you can create your own stream if you only want to do this for particular parts of your simulation, like the customer arrivals, for example. And then, like I said before, you can then put that stream in as the last argument of any random number expression inside ARENA. If you use the stream 10, then you'll adjust the default stream. But if you only want to do the antithetic variates for, let's say, the interarrivals, then you can just say, okay, I'm going to create an interarrival stream, and I will just do the antithetic variates for it. And I'll just have to make sure that in my create block that I put in that special stream, whereas everything else can keep using the default stream. And then you'll get outputs. And so, the outputs that come out of ARENA, you just have to remember that every even output is not independent of every odd output. So then you have to create these antithetic variates. And so you take all of the odd outputs and you pair them up with the immediately following even output. So odd replication paired up with even replication, and you take their average. And so if you have 500 odd replications and 500 even replications, you pair those up and you'll get 500 averages. And then that 500 averages, that is the thing that you treat as the true simulation output that you can end up generating a confidence interval on, doing t-tests on, and so on. That's how those antithetic variates work. All right, so we're probably going to cover the importance sampling then in the next lecture, which will be the last content-based lecture, because the next lecture is lecture L, and then there's Thanksgiving break, and then the final exam review is the week after that. So so that's what's going on there. So are there any questions about the antithetic variates? And maybe what we'll do is we'll just put up the attendance response, and then I'm happy to take questions while it's up. So the attendance question here is going to be, what type of correlation do you try to introduce between, I'll say, consecutive replications in antithetic variates. And so I'm looking for positive or negative. And as we're at time, that's all I've got for you today, but I'm happy to stick around for any questions you have. And for those of you who don't have any questions, I hope you have a wonderful weekend. Oh, I meant to mention the, if you didn't see it already, the course evaluations, they're up on Canvas. I might have mentioned that before. I think they close, I forget when they close, but I think it's before December. So it's like, I don't know, it might be the 27th. I think it's the 27th or the 29th. It should say that. So if you're interested in giving a course evaluation, which I'm always interested in getting those, then please take a look at the link, which is posted right there on Canvas in the menu bar. All right, so any questions from those that are hanging around?
Yeah, so could you just quickly like go over like just a more in-depth definition for like unbiased estimator and like what that means? I know we've used it like a lot.
Right, and an unbiased estimator is an estimator whose so the estimator itself is a random variable and it has its own mean. And so what we mean by that is if you run the experiment multiple times, you'll get different values of the estimator. And so the mean of the estimator, it might be different than the mean of the real system. If those two things are different, then we say the estimator has bias. If those two differences are the same, then we say the estimator does not have bias, is unbiased. So the example we've been given, kind of the easiest example is for transient simulations. So that's not what I meant to do. For transient simulations, maybe I'll lock this on. Maybe we'll do this. All right. So for transient simulations, let me turn this on. We've got, time on this side, and the transient simulation, the actual customer arrival or waiting time might look like something like this. Now for steady state simulations, we are only interested in estimating the steady state value, which is up here. And so this is the real parameter, this state up here. This is our steady state value that's up here. Now, when we run our simulations, sometimes our simulations are going to estimate a value that is here. Sometimes they're going to estimate a value that is here. Sometimes they might estimate a value that's here, sometimes over here. Now, all of these things together have some distribution. So this is the estimator distribution. So this is the distribution of theta hat. Now, if I'm running my steady state simulation and I've managed to get rid of all of this transient garbage here so that all of this here is gone, then I can be pretty confident that this distribution over here, this orange distribution, is going to have the same mean or very close mean as the real performance variable. But if I did not get rid of this transient stuff, then all of this transient junk in my steady state simulation is going to pull down my estimate so that the estimate will actually be down here. So this estimator, so some estimators will be here, some will be here, some will be here, some will be here. So the mean of this estimator will be here. And this difference between the real value and the estimator's mean is what we refer to as bias.
Okay, that makes sense. So basically, in determining whether or not an estimator is biased or unbiased, it's really just comparing like the estimator itself to like what it should be, and if it's like too far off, then it's then it's biased.
Right, yeah. If we were testing an estimator, what we would do is we'd have ground truth on the real population mean, and we could run 1,000 estimations and then look at the distribution of those 1,000 estimations. And if it's an unbiased estimator, then the distribution, that distribution should be centered or should have a mean of the ground truth. If you want another example, it's closer to voting examples. There is that gerrymandering can potentially create bias in voting, and so regardless of how many votes you take, then if gerrymandering guarantees that that one political party gets more electoral college votes than another, then even if there's a 50-50 split in people across the political parties, which would kind of be the kind of a ground truth, you find that one political party has an overrepresented share of the, say, electoral college votes. And so that's an example of bias where you can run the experiment, the vote, over and over and over again, and it's always going to say that one party is going to get more votes than another. But that's because you've introduced a bias in how you've drawn those electoral college votes by gerrymandering. And so the bias is the difference between the estimator's outcome, average outcome, and the real outcome, or the real average outcome.
Okay, that makes sense. Thank you so much.
Mm-hmm. And Abdul Rahman, I saw you were had, I think, a question.
Yeah, I had a pretty random question, which I think might be more suited for 380. But so I'm like trying to understand this Moderna vaccine in the headline.
Okay.
And so I think the numbers were like 90 people, or I'm sorry, 5 people were infected out of 15,000 in the group that got the vaccine, and then it was like 90 people in the control group got infected with COVID. And so I was kind of I was kind of curious as to like this, it seemed like, wow, it seems like such a small difference, but sure enough, I put those numbers into a 2-prop z-test on my TA84, and of course the p-value was actually quite small, like less than 1%. I'm trying to figure out how do they come up with a sample size of 30,000, and how, because I know there's an equation for it that depends on variance and then a margin of error, and then the
That's right.
value. But I'm just wondering, is how did they come up with 30,000 as far as this sample size, and is that going to be representative of? And then they always hang out on this number of 94.5% effective, and I don't know how to interpret what that means either.
Right.
If that's something you could answer for this, or if that's just a little out of the scope of
no,
this.
I think that's apropos. I mean, so I haven't looked in actually in even as much detail as you have at those numbers, and so, but what I can tell you is that they do power analyses just like you did on that homework, and there are even tools like G-Power. G-star Power is a very popular power analysis tool, where if you have some estimate of variance in your population, and maybe you have variance from an earlier trial or other data, or you just make a guess at it from what you know about other diseases, then that's how you guess your variance. And then the effect sizes, that's they have policy where they say we really need to be able to detect down to this size, but if the effect is smaller than this, that's really what's too small of an effect that you want to detect. And so you could say, well, if there's only a 2% effect, I really don't care about that. And so so that can kind of set your effect size. And with those two things, you can use these tools like G-Power, or the power analysis that you guys did back in that homework assignment, and then that will allow you to calculate these 30,000 numbers. And so that's, I mean, it can get more complicated as you get into sort of experiments that, like the power analysis that you did was for a paired t-test, which basically was a 1-sample t-test where you could guarantee all the numbers are normally distributed. And so under those really strong assumptions, the power analysis was very easy to do. Power analyses get much harder as you get into more complicated experiments where you can't make as many assumptions, and there are Monte Carlo approaches and all that, but they still revolve around exactly the same thing you did in your homework. Give me a variance, give me a minimal size, and effectively what they do is they generate alternative hypotheses, and they say if there was an alternative hypothesis that was looked this particular way, would we be able to detect it? And at what number of samples could we detect this alternative hypothesis? So you can generate a simulation of an alternative hypothesis and then see how many simulation runs you need to run until you can determine that your simulation is different than your real one. That's one way you can do a power analysis if you don't have like a simple t-test that you're planning on running. Your other question about like the 95%, where do they get 95%? And I haven't looked in particular, you know, but my guess is that they are estimating the performance of this, and it is a proportion, and they have generated a confidence interval on these proportions. And it might have been you who asked about when you generate confidence intervals on quantiles. That's effectively what they're doing, is a quantile estimation. And there was this question of like, well, why do you use that funny formula for the half widths that has p times 1 minus p? And so it turns out there's actually more sophisticated ways to generate confidence intervals for proportion data that become asymmetric as you get closer to 100%. Because you don't want a confidence interval for a proportion going over 100%. You want it to sort of only go low. Like if you're at 99.9, you want it to go there, down there to wherever, you know, down to 95. And so my guess is that the data that you've actually looked more at is that it is like at 99.9% effective. But if you were to calculate, like there are tools in R that calculate confidence intervals for proportions in a much more rigorous way than the way that I showed you, which is kind of the simplistic way that assumes normality and some other things like that. And if you used those, my guess is the confidence interval that you would get for that proportion that you estimated would go from about 95.1 up to 100. And so they're saying that we have no idea how effective it is in this range, but we know it's at least 95% effective.
Okay.
That is my guess is what they did.
Because I think with the other vaccine that had come out like a few weeks ago or something, they had reported 90% effectiveness.
Right.
But I wasn't really sure how they had, what that comparison is of the, you know, what are they dividing out, you know, to make that an apples to apples comparison, so to say. But
my guess is that effectively the variance or the number of samples was so different in that other one that they could only conclude, or their proportion was slightly lower, and when you took the confidence intervals with that proportion, it drug the whole thing down, and that's why they could only guarantee 90%.
Okay. And usually when we're calculating sample size, you know, the problems we get, you know, might just tell us, all right, this is the margin of error that we want. But you're saying like a margin of error is kind of like arbitrary, and, you know, that whoever's designing the experiment is just saying, we want to be able to detect up to like a 0.02 margin of error, and so that's how they'll come up with the sample size.
That's right. That's right. You sort of say that there is a practical difference size, and if your practical difference size is you use that to determine like how many, because if you want to detect the tiniest difference, you're going to need millions of samples. Right. And so, but you say, well, the tiniest difference is not a good enough effect. So at what level of effect do I really say we have got a good vaccine? And so that's really what you said it at, is I need to be able to detect that effect. And that's how they determine that we need 30,000 people. Plus they have to deal with the fact that, well, not all of them are going to get sick and all that. And that goes into the variance side of the calculation.
Yeah, I was actually—
those are great questions. But my other classes coming in, so I have to, but great questions, and feel free to send more of them or come to office hours or something like that. I'm happy to chat more about this.
Cool. All right.
All right, so for the 325 students,